So we're now going to focus on STL output iterators. I've talked a little bit about them when I talked about input iterators, but I want to give a bit more formal definition of what an output iterator is. So an output iterator is a type that provides a mechanism for storing, but not really reading, the values in a sequence of values. And we've seen an example of this already. I talked about this briefly when we talked about input iterators, which was the third parameter to copy, which is the output iterator, where the results of the copy are going to be stored. And in that particular example, we saw the use of a back inserter, and we'll look more carefully at that in a moment. If you want to learn more about the output iterator category, take a look at the link at the bottom of the slides. You can think of output iterators as essentially the converse of input iterators, but they have a more restrictive interface. They must support, there's some things they don't have. For example, they can't do read operations, so they don't have const operator dereference, but they must support non-const operator dereference. So you can use output iterators on the left-hand side of an assignment statement, but not on the right-hand side of an assignment statement. So again, it's an L value as opposed to an R value. So the intuition for an output iterator is basically like a reel-to-reel tape. I don't think anybody even remembers what a reel-to-reel tape is, but when I was growing up, they were a way to listen to music at a more high fidelity than using a cassette tape or an 8-track tape or whatnot. And you can basically think of this where you can write the value on the tape and advance to the next location, but you can't read anything and you can't back up or rewind. So you can only write. So it's kind of like copy only as opposed to read only. So we're going to take a look at an example here, and this is going to kind of look at the back inserter part that we have touched on earlier, and then we're going to round off our example of copying data. So let me go ahead and change my view. So what I have now is an example which will illustrate output iterators. It'll actually illustrate the combination of input and output iterators, and just reiterate what we just talked about. So an output iterator can only be used for writing. So what that means is you have constructor, you have an assignment operator, you have a dereference operator, but can only be used on the left-hand side, not the right-hand side of an assignment statement. And you can do pre and post increment, plus, either side of the iterator. Many algorithms like copy, like transform, return output iterators as the result, which enables these operators to be basically chained together if you need to chain them together. So we're going to take a look now and refocus on our earlier example, except now we're going to focus on the output iterator part of this, and we're also going to complete the example so it actually does something useful. So as you can see, what we're going to do here is we're going to have an initially empty vector, and then we're going to read from standard input using our input iterator adapter, the iStream iterator we talked about before. So that's going to be the input iterator. And then the output iterator here is going to be the back inserter. It's going to be what's returned from the back inserter, which is going to turn the vector into an output iterator. So again, remember how copy works. Copy goes from basically the beginning of the input iterator range to the end of the input iterator range. And then it goes ahead and assigns each element in the input iterator range to the output iterator, which in this case is going to be decorated by the back inserter. And as we saw before, back inserter is a very clever factory method that wraps a container reference by creating a back insert iterator object. And you'll notice that the reason we have the back inserter method is because functions or methods in C++ can do type deduction, whereas classes and structs cannot. So we don't have to actually put in the type here. The compiler can deduce that. If you look at back insert iterator, you'll see that that is also a class, which is parameterized by container, and it stores a pointer to the container that we're going to be back inserting. And then if you take a look down here, you can see the constructor will stash away that reference as a pointer here in the constructor. And then if you take a look at the assignment operator, as we've talked about earlier, it'll go ahead and take each element that's passed to it and push it to the end of the container. So that's the way that the output iterator adapter is defined here. Make this look like an output iterator for the purposes of the copy algorithm, but in fact, it's really pushing the elements to the end of the container that it's holding. And I think I mentioned before that the operator dereference and the plus plus operations are just no ops. They don't do anything. They just are sitting there to make the copy algorithm syntactically viable. So after we've copied the contents of the standard input treated as ints into the initially empty vector, we have a vector full of these elements. And now what we're going to do is we're going to copy the contents of the vector from its beginning to its end using the mechanisms here, which are the factor methods that return the appropriate iterator, which in this case could be a const iterator. And then we're going to go ahead and use another iterator adapter called an OStream iterator. And that will allow us to take C out, which is standard output, and convert it to work with the contents of the vector using the copy algorithm. So OStream iterator creates basically an output iterator. It's an output iterator adapter that makes standard output work in a way that looks like an iterator or an output iterator from the point of view of copy. So let's go take a quick look at OStream iterator. OStream iterator is kind of the reverse of iStream iterator in that it holds the OStream that we're writing to, and it keeps track of the string, if any, that we're going to use to separate each of the values as we write them out. For our example here, we used the new line as our separator, but we could put a space easily. And then down here, you can see that we have the constructor stashes away that value. Whoops, that's in the wrong place. Let's go back over here to OStream iterator. And it's going to stash away that OStream and the character string that we pass it, the const char star. And then its operation down here, its assignment operation is going to take the value, which in this case will be the elements that are in the vector, and it'll go ahead and it will write them to the output stream, followed by whatever we have here, which could be the separator that we've got. All right, so there's also other ways of doing this. We could also use various types of loops. We could have a for loop that uses iterators explicitly, or we could use a range-based for loop. I'm going to focus here just for kicks because we're talking about output iterators. We're just going to talk about the version here that uses the C out. I'm sorry, the C out and the OStream iterator. So let's go ahead and run the program. So it's waiting for me to type some input. So let's give it 10, 20, 30, 40, 50, and then Control D, and that goes ahead and then dumps the contents that we read into that vector. So nice, cool little example. This is probably the way that your typical STL developer would likely write this code, although maybe nowadays they'd be more tempted to use the range-based for loop because it's even more concise. But it's a good example of differentiating between input iterators and output iterators and showing how the copy algorithm allows us to copy from the input to the output, and then we can use various types of adapters to take other elements of STL like C in and C out and vectors and so on, and adapt them to work in the context of what copy expects.